This video is about induction motor start delta starter. It is a well-known fact that induction motors do take a high starting current as high as 5 to 6 or more times the running current. It is this high starting current of induction motors that necessitates the use of a start delta starter technique. So please do subscribe to my channel and follow me in this video to know what really happens scientifically when an induction motor is starting and when it is running. Moving on. These are the diagrammatic representations of what really happens when an induction motor is starting and when it is running. When it is starting, the windings are connected in star, and when the induction motor is running, the connection automatically changes to delta connection. That is after the induction motor must have started. So let us look at the characteristics of the induction motor when it is starting and when it is running. So here we go. This is the star connection for starting process, and this is delta, which is for the running stage. Now here we have the line voltage being 400. It is the same line voltage that is being applied when it is starting and when it is running. So what is the real essence of using start delta starter? One of the reasons is that we need to reduce the starting current so that it doesn't disturb, the starting does not disturb other loads that are connected to the same bus section in the installation. So we want to see a situation where the motor is starting with reduced current, especially phase current, and then after starting it changes to the delta connection where the motor draws more the current, and at the same time it has more apparent power. So here we go. This is a balanced motor, a motor with balanced windings. So Z is the impedance of the windings, or each of the winding has Z as the impedance. So this is a V phase star, V phase delta. This is red, yellow, blue. Those are the three lines: red, yellow, blue. So for the starting, we apply this voltage. This is the line voltage, and let's see the phase voltage will be 400 divided by √3. So now here we have, for this one, we have a V line star. So it being equal to V line delta. This voltage here is the same as voltage here. So, and it is 400 in each case, because you don't change the voltage supply during or after the starting. You don't change it. So now we have what about the phase voltage from here to here? This V phase delta, star. So V phase star is equal to the line voltage divided by √3. And then for the running, we have V phase delta being equal to, because for delta connection, V line is the same thing as V phase, so it's 400. So now if you divide this by this, what do we get? We want to compare the two voltages. So you now have 400 divided by 400 over root 3. So, and this is what we have, and if the mathematics is well done, it will be root 3. Now, what we are saying is that if you divide the running phase voltage by the starting phase voltage, you get root 3. And we have this mathematical relation from there, that is V phase running is equal to root 3 V phase starting. Or if you take it, you put the value of root 3 there. Root 3 is 1.7321. So it means V phase running is equal to 1.7321 V phase starting. So what we are saying is that the phase voltage for the starting is reduced, or is smaller than the phase voltage for the running situation, or the running stage. And from here we can also infer that V phase starting is equal to 0.577 V phase running. So that means when it is starting, the phase voltage that will be applied, that is applied to the winding, each of the winding is 0.577 times its value when it is running. As I said before, without the use of star delta starter, so we'll have started the motor using delta connection, and the current will have been very high, up to 5 times or more times the running current. So what we are saying here now, by introducing the star delta starter, let's see how far the starting current will be reduced, or what will happen when it is starting, making use of this starter. So let's calculate the phase current. This is the phase current here, and this is the phase current here. Okay, so let's calculate it. We have done that of the phase voltage. So I phase for star. Star means starting. So which is the star connection. So we have the current the voltage applied divided by the impedance, which is this. And for this, the current is the phase current is the phase voltage. The phase voltage is the same thing as line voltage, so which is 400, and the current is 400 divided by the impedance. So we divide this phase current by the phase current for the star connection. We have this, and the result is root 3. So which means if you cross multiply, you can have I phase delta, that is I phase running, is equal to root 3 I phase starting, which is the star. So again, we've been able to establish another mathematical relation, meaning that I phase running, so this is I phase running, is equal to root 3 I phase starting. It's just like the one that we did before, or if you twist it, you can have I phase starting is equal to 0.7, and I phase starting is equal to 0.577 I phase running, which means when it is starting with the introduction of the starter, when it is starting, the starting current is like around half of the running current. So that is about this one. So this is the second mathematical relation, and we move ahead. Alright, we've been able to derive mathematical relationship or mathematical relations for the phase voltages, that is the starting phase voltage for starting, and phase voltage for running, and also the phase current for starting and phase current for running. So what about the line current for starting and line current for running? So here we go. The phase current here is 400 over root 3 divided by the impedance. So since in delta connection, the phase current is always equal to the line current. So this is the line current. For here, this phase current is 400 over 400 over the impedance. This Z times root 3. That to get that's the phase. 400 over Z is the phase current. So to get the line current, you multiply it by root 3, and you will divide this by this. We get 3, and we come to a conclusion that the IL delta, that is I line running, is equal to 3 times I line starting, or you can have I line starting is equal to 1/3 I line running. Now let's look at the apparent power for the two situations, that is for starting and for running. S is the apparent power. So apparent power for the starting is this: root 3 times V line starting multiplied by I line starting. So which is this. And then for the running with delta connection, the apparent power is this. And then if we divide the running apparent power by the starting apparent power, we have this, and the result is 3. So we can now infer that the running apparent power is 3 times the starting apparent power. So here we have 3. So, and then please remember that star is for starting and delta is for running. So S running is equal to 3 times S starting, or you can say S starting, that is apparent power for starting, is equal to 1/3 the apparent power for running. Therefore, looking at this diagrammatic representation, so we can infer that, or we've been able to infer that the S delta, that is apparent power for running, is 3 multiplied by apparent power for starting, making use of this star delta technique. And also I line delta, that is line current for running, is equal to 3 multiplied by line current for starting. And also V phase delta, that is phase voltage for running, is root 3 multiplied by phase voltage for starting. And also I phase delta, which means the phase current for the delta, which is running, is equal to root 3 the phase, or times the phase current for starting. So therefore I phase delta is equal to root 3 I phase star. And finally, please do subscribe to my JK Multimedia Solutions, and expect more wonderful videos. Thank you.